so much for coming. And if everyone can just mute while he's talking, that would be awesome.
Okay, thank you so much, Leah. All right. So, first of all, before I start my presentation, I would like to acknowledge the Wadawurrung and Bunurong people, who are the traditional owners of the land in which I conduct this study, the Werribee River, also known as the Werribee River, and the surrounding lands. I pay my deepest respect to their elders, past, present, and emerging, and recognize their enduring connection to this landscape and country. So yeah, I'm not really sure how many of the audience here are from Victoria, but maybe I'll just give a little bit of a brief on the area that I'm actually presenting on. So this is Werribee. It is a little suburb located west of Melbourne. It is generally known for its tourism. So like there's this cool little zoo that looks like mini Africa or some sort. There is the mansion. There is some rose garden, which I think has stopped blooming by now. It's autumn. And there is the golf club too, if you're into those. But I believe we Argonauts prefer to look at this one right here. This is the Cairo Cliffs. This has this long set of outcrops featuring interesting layers of sedimentary rocks, or sediments to be precise, given it's not yet a rock per se. And it is considered one of Melbourne's geologically important sites. So that might look like the only geologically interesting feature here, right? Like there's only one point, there's some river, and that's it, huh? But if we were to look at it from another lens, let's say from a high resolution digital elevation model, bam, we suddenly see way more things going on. We see there is this channel here and there, there's a valley over here, there's so many things going on all of a sudden. So that is what I'm going to do today. I'm going to show you a part of my thesis essentially, and it is also in collaboration with Afifuddin, a colleague from Australia Awards. And yep, I guess I'll just get straight to it. So maybe a little mini disclaimer, given I don't know how many of us are like true regular geoscientists, or maybe there are some geoscientists that study deep time. Well, we know that the Earth has a long history, and usually geologists prefer to look at, I don't know, the entirety of the Phanerozoic or like the older time periods. This presentation will just look at this teeny tiny eon called the Cenozoic and this teeny tiny period called the Quaternary. It is like the last 2 million years of the Earth's history. And this study is actually going to focus like on this small bit, which is, yeah, I know it looks like it's so insignificant to the entirety of the Earth's history. But trust me, this short time period has a lot going on. Like the Earth has changed a lot in that short period of time. Like in the land where I'm studying, megafauna used to roam on the land. There might be some ice going on too, who knows? Because after all, in this time period, the Earth has changed due to the Milankovitch cycle, due to the Earth still changing around. So we have these periods of warmer periods called interglacial and the colder period called the glacial. A lot of things has changed really, even though it's really short. So the problem at the moment is that we are currently at the interglacial, and we are in for quite one hell of an interglacial because we are having some anthropogenic climate change essentially. So the Earth is warming quicker than it should. But worry not. If we were to look at the past, the Earth has warmed even more than the present day, which please, I do not want it to warm anymore. But we can see in the past that it has received even more warming. So we can try to look into the past and see how the landscape responded to such thing. Because at the moment, we are facing some serious threats. So having some insight on how it was in the past, how it responded there, can give us a little glimpse, or a little spoiler essentially, on what to do or what to expect if the Earth warmed by a bit. In this case, I'm going to use rivers as a way to look back in time, because rivers are, interestingly, very responsive to changes in climate. I like this diagram here of the rains relationship. Well, the original relationship is like this mathematical equation, but having this represented as a scale like this is really amazing. It makes it much more intuitive. So in this case, it is representing these, how do I put this? It's kind of like the balance between a river stream between the sediments that it carried and the water power, essentially. If the river, for example, tips towards this side, so it has more sediments, for example, or the sediments are chunkier, we can expect that the river will start to deposit new stuff, essentially aggradation. On the other hand, if this side were to tip and we got more stream power, maybe the stream is like having extra water discharge, or maybe the slope has increased, we will expect that the river will become more erosional, it will become degradation, essentially, where instead of forming new landforms, it will carve through the existing landforms and form valleys. So this essentially gives us a little way to guess, or to have, at the very least, look into what probably caused it. Is it the climate, or is it the sea level change? Yeah, essentially, this is like a little clue in our little detective game. Well, as for the location, the Werribee River itself may seem like a standard river catchment. Like we have like around 7 tributaries feeding the river, and then all the sediments are dumped away into the sink, which is this yellowish bit called the Werribee Delta or Werribee Fan. But if we were to look into the Werribee Fan, well, it has been carved away. That is why the carrot cliffs exist. So we have this alluvium that we can see nowadays, which means something has changed. And additionally, we see from the LiDAR, or from the high resolution DEM that is, that there's a lot of things going on too besides that. So there's a lot to tell. And honestly, there's a lot of significance to it too. First of all, of course, it will add our information or knowledge base about the geology of the area, which could be pretty cool if you are trying to build a geosite, in which I believe it is already trying to be that way by the Windham government. And there are also some interesting finding of megafauna fossil recently discovered by people at the Melbourne Museum that hints to the existence of the megafauna that I talked about in the intro. So by understanding how the river was in the past, we can pretty much see how the environment was for these giant guys. And also, this area is the lifeblood of the Aboriginal people in the past, that is the Wadawurrung and the Bunurong people. And we have found Aboriginal scatter across the river too. So if we found something very recent, we can pretty much tie it back to the way the Aboriginal people grow on this wonderful landscape. On the opposite side, as I have been emphasizing in the temperature part, as we are facing climate change, things are shifting too. There are issues with flooding, with the area facing erosion to it at some site. So all in all, the river poses some risk to the community, which is why there is this Werribee River Association being formed. And I believe having some insights into how the river has been behaving in the past can pretty much give us a glimpse into how it will behave now and in the future. Now, to achieve that, of course, we need some toolbox, some tools essentially to pretty much read into the landscape to understand how it behaves. In this case, I'll be using these 3, using the sedimentology of the outcrop itself, using some high-resolution DMs, and some geochronology. I believe the sedimentology part is already quite obvious, and I'll be explaining these 2 instead. First of all, we'll go with the DEM, the digital elevation model. So essentially, we have a high resolution DEM nowadays compared to years ago, since we have the LiDAR technology, where we can fly some drones or airplanes across the area, and we'll get some very high resolution elevation models there. Like the top one here is the SRTM. So the resolution here means that 1 pixel is around 30 meters. Nowadays, 1 pixel is like 5 meters. So we can see much more detail. Like in the past, like it's really, really blurry. We cannot even make out this part right here. Now we can see there's a lot more channels going on. And other than that, we now have much more understanding about luminescence geochronology, which is a unique way where you do not need like carbon isotopes or the like of it. You can just rely on the quartz or feldspar grains that are already exist in the sediment and try to use the amount of energy that has been stored within them during burial, where the amount of energy that it has trapped inside of the crystal lattice is more or less can be used to know the age of the sediment, essentially. So combining what we can obtain from DEM and also from the outcrops, we can pretty much get information on like what landform are there, what are the relationship between one landform to another, what are the contexts behind the formation of the landforms. Is there a certain time period in which this unit is tied into? And at the moment, I'm also trying to use some extra geochemistry to understand the paleo environment too, which is still underway at the moment. And we can also tie it back to the global temperature and sea level changes so that we can pretty much know how the Werribee River evolves throughout time. For the methods, I won't really put this into detail, but to put it very simply, we will have to do the DEM processing, in which we turn the DEM, which originally measures elevation above sea level, to REM, relative elevation model, in which it shows the elevation above the river itself. This will greatly enhance the feature that we can see, as we can see from this picture here. And from there, we can try to delineate the features and try to conduct some bathymetry analysis. And from there, we can also do some interesting statistics to see if there are some specific attributes to a certain landform. And of course, we can also do the geochronology with the field samples too, which was using the luminescence method I mentioned before. Right, without further ado, let's actually go to the results. So first of all, we can turn this digital elevation model to the REM, which now shows the features in greater detail, and start delineating the features, in which we can see that there's a lot of things going on. And if we were to make REMs from the channels that we are delineating here, we can make more kind of like maps of elevation relative to the channels, which shows the features tied to them in greater detail too. Like for example, let's look at this one right here. This one here is one of the channel or paleo channel here that is over here. Right, I think I forgot to mention that the current river is this one. So whichever we see here are like abandoned channels, essentially. So this channel right here is showing a higher elevation around the channels. And if we were to look at it from the cross section, it's pretty much symmetrical. This can be interpreted as some form of an overbank deposit, a levee or some sort, where it is the result of the river flooding and then depositing sediments across the edges of the channel and then repeating it over and over again so that we get this elevated bump around it. Can also look at the modern river channel too, where we can see that there is some steps, essentially some levels between the top area to the main river itself. These are some river terraces, which, well, it's become even more clear when we look at the cross section of it. And generally, this shows that they are unpaired. Like there is no pair for this one, there's no pair for this one. So it is likely that the river loves to meander, or not meander, essentially, like to horizontally move from one side to another. So we ended up not having a pair of terraces. And we can find a combination of both in this area over here, which is pretty much another incised valley similar to the one that forms the Carrot Cliffs, but it has been filled with a channel that has formed this interesting meander and overbank levees similar to the one that we saw previously. So that's what we can identify from the REM. There is also another dataset that I would like to look at. This is the Bathymetry DEM, the result of the Victorian Coastal Department. So from the bathymetry data, which goes into the sea, yes, this over here is on the sea, we can see there is this area that is noticeably lower than the surrounding, and it forms this interestingly valley-shaped topography. By looking at the REM, I suppose it can be seen more clearly too. I interpret this as the extension of the valley that we are seeing in Werribee, which probably marks when the land used to be extending much further seaward back when the sea level was much lower. And additionally, in the area, we notice that there is this area that is relatively lower compared to these two channels or valleys. I assume this is the result of the sea level rising really, really rapidly, so that the valley over here is quickly put into deeper water depths and therefore less energy to erode it out. And then this area, which is now the shallow sea, is the one that is getting eroded rapidly, which is why it became lower relative to the entirety of the river valley. Now to the actual mathy stuff, essentially. Please do not be scared. This is hopefully very simple. So what I'm looking on for now, it will be two parameters that I find the most interesting. First of all, it is sinuosity. Sinuosity is essentially how curvy or how squiggly the channel is. And the channel width is pretty much the width, the width of the channel itself. So the eastern and the southwestern paleo channel here are noticeably much thicker and also pretty squiggly or meandering essentially. Meanwhile, the western paleo channel, the one inside of the incised valley, seems to be somewhat thinner, and it is also meandering too, but not to the same extent as the two other paleo channels. And lastly, the modern river is generally the least sinuous, so it's more straight, and its width is pretty much varying from one side to another, which I suppose makes sense given it is getting thicker closer it is to the sea, essentially. And we can try to also order the features too, based on the way it cuts to one another. So for example, the incised valley that we talked before, so you can see it kind of like cuts through this southwestern paleo channel right here, which means this valley is most likely younger than the southwestern paleo channel, just like how the Werribee River cuts through it. So like we can kind of see a relationship between one to another. So in a sense, we can pretty much order it from oldest, which is the bottom part right here, to the youngest features. And given we know that we see some depositional features like the levees on the eastern and the southwestern paleo channels, we can pretty much deduce that there are some of these units are more gradational, and there are some that are more erosional that cuts through and form valleys and terraces, which pretty much is like this, where we have lots of aggradation during the eastern and the southwestern paleo channel period, some aggradation after the formation of the valley that forms the meandering stuff that we see inside here, and then the degradation that we're seeing at the moment. Also, we can try to look at the elevation of each of these terraces. And based on the stages of the terraces, that is the older to the younger one, it seems that the trend is that the terraces are getting shorter and shorter over time, which might mean that there might be some shift going on. Maybe degradation is not the end of it. Maybe we are shifting away from this degradational period that forms the valley. As for what we can see from the outcrop itself, well, this is a panoramic view of one part of the outcrop. And essentially, this area here was identified to consist of three different units. We have Bedded Cliffs A, which is the bottom area right here. Bedded Cliffs B, which is this tiny, tiny bits over here, the tiny, tiny bits of beach. And Bedded Cliff C, which this top part that also noticeably got thicker and cutting through the older units over here. And each of these units are divided by this reddish paleosoil, ancient soil essentially, that marks when the unit just stopped depositing itself, because entering a hiatus of some sort, and then we got some soil formation on top of it before the deposition of the next unit. So here it is, the full layout of the outcrop. And in this case, I have done some geochemistry with this, some ICP-MS to do some analysis of the paleo-environmental proxies. And I think the most interesting one is that the transport energy between each of these units differs slightly. Namely, for unit B, it seems to have higher energy, transport energy proxy compared to the others, which is represented by these elemental ratios. Now, we also conducted some ongoing luminescence dating for these, where we have identified the age of the units that are observed in the cores that are taken around the township and also in the outcrop itself, which I guess it makes sense from here, but I guess it would be better if we show it to the chart that we saw in the intro, the one that shows the temperature and the sea level change. So unit A is mostly around this 150 to 200,000 years ago period. Unit B is just this tiny period over here, and unit C is over here. And now that we have gathered all the clue, let's try to piece together what's going on. So unit A and C, which are the thicker units, seems to coincide in conditions when the temperature are lower, which are a little bit odd because usually we expect more deposition during warmer periods, but this time it's during colder periods. So in this case, I interpreted that the colder periods may lead to less vegetation, and therefore we may have more sediment supply that can enter the stream, and therefore we have much more thicker deposits. And additionally, maybe the sediments here, the rivers also acted more steady, given we see that it has these lots of meandering channels along with the overbank deposition. And it might be of a lower energy too from the paleo-environmental process that we showed before. And then we also have the erosional or hiatus period, which this is not necessarily from the geochronology, but I suppose this is when it makes sense. For example, the border between MIS 6 and 5 over here probably marks the noticeable sea level drop that may cause the deposition to end altogether. And the most recent sea level drop during the last glacial maximum might be the reason the land extends very far away so that we can see that there's a valley really seaward, essentially. And then there is the transgression period, which in this case, unit B seems to coincide in it. In MIS 5, essentially, after the sea level drop, the temperature rises, the sea level rises too. And noticeably, we have the unit B seems to be quite an odd one because we have this thin unit that seems to be forming in higher energy. And I assume from there, we probably can guess that it is probably more flashy or more like abrupt and more sudden, more sudden essentially compared to the unit A or C. And the result of this transgression is also what we are seeing in the combination of RDEM and bathymetry data, which results in the area over here being carved away by the shallow sea process energy. And we have the in-betweens that we do not really observe, which may be the result of probably has been filled of some sort. But yeah, I believe from here we can already tell quite some story too. Like on colder periods, we will have some steady deposition through meandering channels. On sea level fall, we'll have erosion going on, or maybe there's some hiatus that forms the paleosol and the valleys. And during transgression, we can expect more sudden kind of streams forming on, which ties to the present day because we are facing some transgression after all, and we are facing through the climate change too, which will exacerbate the issue, which may mean that we'll have to focus on the flooding issues that have been going on through the area, especially in the flashy part of it, because the suddenness can certainly cause some surprise damage to the area, which I reckon it actually caused some damage to the Werribee part too, like the collapse of the bridge that requires the repair that I saw like in last year or so. And honestly, this research is still ongoing. We are still going to implement more information that we can gather from geochemistry, from more sedimentological analysis, and also from more geochronology, from more samples that we have. We still have like a dozen more samples to look into the geochronology on, after all. And that's pretty much it. Thank you.